when we talk about PC, it's not personal computer, it's actually Portland cement in the context of civil engineering or architectural engineering materials. And whenever you say just cement, people normally mean Portland cement. This is not the only type of cement available. It's worth knowing. So, people typically use the terms cement, mortar, and concrete interchangeably. But as engineers, you need to be careful. These are different things. So cement paste is cement and water. And cement paste is, you can think about it as the glue, which glues the aggregates together to make concrete. So that's what it is. Cement by itself doesn't have any gluing effect. You need to mix it up with water. What is mortar? Someone knows?
Cement, water, and sand.
Exactly. If you add, it's important, but not that important. It's not that important, but it's cool. Okay. It's important. I hope you remember that mortar is not the same as cement. So you hear people saying, "Oh, I cemented my driveway." No, you didn't cement your driveway. This is wrong to say. So as your colleagues from Pittsburgh or around were saying, yes, I remember. Just kidding. It's okay. It's good to laugh in the after. I like energy more than if you don't have any energy, like some days where whatever I do, there is no energy. Anyway, this is better. Cement, water, and sand. And sand, when we talk about sand, we don't necessarily mean like sand in the sense of soil mechanics. It's more like fine aggregates. Whatever passes through number 4, sieve number 4. And concrete. So what is the difference between mortar and concrete then? Yes?
Concrete has stone as well.
Exactly. So we call them not stone, well, maybe here, but it's coarse aggregates. So let's, so as you can see, the aggregates, actually sand, like fine aggregates and coarse aggregates, make up a major part of the volume of concrete. And cement is much less. And then you have some water, and of course you are going to end up with some air voids. And you see that you also sometimes have to add admixtures to get some exotic properties. Almost all the modern concrete mixture have some admixtures. So this is pretty much what concrete is, and we are going to focus today and on Friday on cement before moving to the design of concrete mixes. So I'm just waiting for everyone to write down. If you just came, there is a new packet. Okay. We move on. So I want to show you a short video. This time I chose a very short video to show you how the cement production is. Please pay attention to remember the main steps. It's very simple. So hopefully it's all going to work. It worked in the morning. Wow. Okay, wait. That was interesting. Why is it that way? So this was perfectly fine this morning. I may narrate it myself if it doesn't work. So let's see. Let's try again, change the cables. Okay. Okay, please keep quiet so everyone can listen.
Million tons of cement is produced here at Hope Works every year. The site employs around 180 people and has a strong safety record. It also prides itself on being a good neighbour and has long-standing links with the local communities in the surrounding Peak District National Park. Cement is a versatile construction material. It is the essential ingredient in concrete, the world's second most consumed material after water. Concrete is made up of cement, water and aggregates, rock, stone or gravel. Hope is renowned for its consistently high quality, including light coloration and strong performance. But how is it made? The process to manufacture cement is complex. It relies on ensuring all the right ingredients are combined at the right temperature. Just like baking a cake, the chemistry has to be just right. And the process starts here in our two quarries. Limestone and shale are the key ingredients for the cement mixture. This is the limestone quarry, which is 1.5 kilometres long, 600 metres wide, and 170 metres deep. At any one time, there are around 30 working faces, measuring approximately 4.5 miles in total length. This rock here was formed 330 million years ago. Now 2 million tonnes of stone is extracted here every year. Shale is the other key ingredient, as removed from our other quarry by heavy machinery, through a mobile crusher, and into the stone store. We also used pulverised fly ash, or PFA, as a part replacement for shale. The chemical composition of PFA, a byproduct from coal-fired power stations, is very similar to shale. As the quarry progresses, the worked-out areas are gradually restored, giving them back to the natural landscape as part of the conditions of Hope's planning permission. Over 13,000 trees have been planted since 2003, and the company works with nature organisations to ensure the restored land encourages a wide range of wildlife for the future. Falcons, rabbits, stoats, ravens and hare are among the animals found in the quarry. To access the rock, controlled explosions take place around 100 times each year. Each of these blasts produces around 20,000 tonnes of material for Hope to use in the process. Skilled operators move the stone from the blasted areas so that the rock can be crushed. Some of these giant dumpers and diggers cost around £800,000 to buy. A new type can cost up to £16,000. The rock is crushed 3 times, from 1 metre down to stones smaller than 20 millimetres in diameter. The primary crusher can get through 1,400 tonnes of rock every hour. The second and third crushers process around 1,000 tonnes per hour. The stone is transported via conveyors to the works, where it's held in the stone store. Now we move to the works itself, where the quarried stone from the limestone and shale quarries and other materials are put through a chemical process to produce the ultimate product, cement. The stone from the quarries is transported to mills to be ground into a fine powder. In a tunnel beneath the stone store, limestone and shale are mixed together and moved on conveyors to the mills. Each of these mills holds 205 tonnes of steel balls, which grind the rocks to the required powder size. The raw material powder, or raw meal, is then transferred to a blending silo before being blown to the 6th floor of the building, the preheater tower. You can see the cyclone tube structures inside the tower. As the raw meal moves from the top cyclone to the bottom, it heats up from 80 to 830 degrees in just a few seconds, preparing it before it goes into the next and most important stage of the process, the cement kilns. The kilns are the heart of the manufacturing process. There are 2 at the Hope Works, each is 70 metres long and 4.8 metres in diameter. These giant steel tubes are lined with special heat resistant bricks, over 70,000 per kiln. Each kiln is turned 2 revolutions per minute, resting on giant rollers and powered by an electric motor. The kiln operation makes up a large proportion of the works' monthly £1 million electricity bill. As the cooked materials travel from the preheater cyclones into the kiln, it's heated up even further to more than 1,500 degrees Celsius. At this temperature, the limestone, shale and fly ash combine mechanically to form a new type of mineral substance, cement clinker, the properties of which are key to the cement product's ultimate performance in construction. In order to reach these temperatures, the process needs a large amount of high-energy fuel. In the past, this was just coal, but now Hope uses a wide range of fuels, making positive use of processed waste materials such as scrap tyres and domestic waste. Around 35% of the plant's fuel now comes from more sustainable waste sources, helping reduce its environmental impact and keep the bills down. The 132-metre-high chimney provides a local landmark, but it also plays a vital role in ensuring Hope Works is as environmentally friendly as possible. Emissions from the kiln process are controlled and monitored through high-tech equipment connected to the chimney. The company operates to very strict limits on emissions, which are governed as part of the site's overall environmental performance by the regulator Environment Agency. Through a central control room, an expert team can keep an eye on all aspects of the process, including 24-hour monitoring of the emissions. Continuous investment in new technology for our environmental protection systems ensures we can plan for the emission standards. Back to the cement. The nodules of material which may be built are called clinker. These are cooled very quickly from 1,400 degrees Celsius to less than 150 degrees, and then moved to the clinker store. Once cooled, it's stored and then ground in cement mills with important additives for the final cement product, such as gypsum, which controls the setting process. From the cement mills, the more familiar cement powder, the final product, is transported on to our customers. As part of the overall process control and commitment to producing a high-quality product, sampling and testing takes place at each stage of the process and not the finished product. Cement is transported from Hope Works in two ways. Around 1 million tonnes leaves the site each year via the rail network, and one Hope's depots where it's transferred onto lorries for on delivery to customers. Completion of a major rail investment program in 2008.
Okay. So what are the main, try to write down what the main steps are in production of cement. I think it's in your next slide. So what are the raw materials you have? Before we write, let's just review that together. So what else? Fly ash, right. And then what happens to them? You crush them. Do you remember the size? Almost less than 1 inch. 2 millimeters, less than an inch. And then what happens then? Exactly. And then afterwards, where are they heated? Do you remember the name of the kiln? Exactly. And the temperatures can be very, very high. You heard what numbers? 1500 degrees C, which is really, really high. And what is the output of the kiln? Clinker, right? Those kind of balls that we saw. And then what happens to them? We grind them to get cement. So these are kind of the main processes to get cement. So these are part of the lectures. That means that you may have questions, etc. There is another one that we don't look at in the class. It's just 5 minutes. I made sure that these videos are short this time. So if when you review the material, just take a look at that also. It's kind of a different presentation, but pretty much the same kind of material. So try to write down for yourself the summary. Just take 30 seconds to write something down based on what you heard. And you saw that there is also a lot of emphasis on environmental impact, because cement production is one of the major contributors to the greenhouse emissions. So there is a big push to reduce that and also to lower the cost of fuels. 30 more seconds. How many of you have seen cement when taking it out? So it's a powder, right? It's a powder, grayish, very, very fine. So if you want to look at the main steps in a diagram, this is from your textbook, so you can look at the details there. You see that you mix, let's say, clay or shale, that both works, limestone, you crush it, and then you saw how they are being carried over, and then you basically feed them into kiln, and then you get clinker, which will be cooled very, very fast, and then you add gypsum. Anyone remembers what gypsum is doing? What is its function? Exactly. So we haven't talked about what exactly selling is, but that's the country's gaining the strength because it has a lot to do with cement properties. So gypsum is added, and then you get cement. In the old times, people were using a wet process where they would use water to mix things up better, but now this process is being abandoned because it's very energy intensive. So you don't want to do that. And what I showed you, the dry process, the modern process is more common. So the reason that you have limestone and shale or clay is because you need to have two main ingredients for cement. One, you need to have calcium oxide, and you need to have silica and alumina. The oxides of silicon and aluminum. And they can have different sources. So you saw limestone and shale, it could be clay, and we looked at the quarries. Now, this is how a kiln looks like. You see that the temperatures go very high up, and at different stages, as the temperature is increasing, we're going to have different compounds. The output of kiln is clinker, which you saw in the movie. Yeah, in Fahrenheit, it's up to about 3,000. Maybe you have more feelings about Fahrenheit than centigrade. So these are how the clinkers look like, and then you basically grind them. Do you remember what was inside these mills? Steel balls, right? They crush them, and look here, you are going to have very, very fine powder, which passes sieve number 325. And then you add gypsum to control the setting. And then you grind. So the fineness of cement is an important property of the cement. And it is measured in terms of surface area per unit weight. So the more surface area per unit weight you have, your material is finer or coarser. If a material is finer and you have, let's say you have 1 kilogram or one pound of two materials, if you have more surface area per weight, is the material finer, smaller, or coarser, larger? Finer, right? If you have 1 pound of rice versus 1 pound of plums, the surface area of rice would be much larger than the surface area of plums. So typically you see that it's being expressed in meters squared per kilogram. And why do we care about it? Because remember, you need to mix cement with water. blue. So if you have more surface area, you have more surface interface between water and cement, so it reacts faster. It's a very, very important property. And if it reacts faster, it means that your concrete sets faster. So if you are making your driveway, it gains the strength faster. You can walk on it sooner. Right? We'll talk about this setting a little bit more, but just to give you an idea. And how do we achieve more fineness? You just grind it for longer time. How many of you have ever grind coffee? That's great. It's like the running exam. You do. So if you do espresso, whatever example I want to bring doesn't work. If you want to make espresso, normally you want to grind this longer because espresso particles should be smaller. When I was your age, I also didn't care about any of that, but there is a difference in this. Anyway, if you grind something longer, it becomes smaller. And this is important. And you saw one example of a cement plant. This was hope that you saw with some information, but I hope that you saw that it's a major operation. It's a big plant. It works continuously. You have several shifts who work. It's very expensive. There are only about 200 in the US, and they produce a large amount of material. And it's about, let's say, 5 cents a pound. This looks cheap to you, but because you need a large amount of this material, at the end, cement is the most expensive component of concrete. What is important for us is to understand a little bit the chemical composition of cement. So you see that at different temperatures, you are going to have different compounds formed, and we want to see what these are. It turns out that cement has 4 main compounds. One is lime, which is calcium oxide, and that's why you need limestone, for example. Then it is silica. Then it is aluminum oxide, alumina, and you also have a little bit of iron oxide. Now, inside cement, you don't have them as simple as you see up there. You have a combination of them. And for example, you have tricalcium silicate. But engineers have come up with the shorthands. So what you saw in the kiln, the formation, are these shorthands. C3S, C2S, C3A, C4AF. And then, depending on your cement, you are going to have different weight fraction of each of these compounds. And this is super important, how much you have of each in defining the properties of the cement. And we want to look at that. So, why it is important? The first 4 react with water. So, these 4 that you have here. And this reaction with water is called cement hydration. And this is the main mechanism behind concrete gaining strength, right? If you have ever worked with concrete, you know that when you just mix it, it cannot sustain weight. If you step onto fresh concrete, what happens? You sink in, right? You need to wait for it a little bit to gain strength. And what causes strength is the process of cement hydration, as we will learn here. And the fact that these reactions are exothermic, probably you've seen in thermodynamics, that means it generates heat. A cement plant report, a mill report, looks something like that. And as you can see, they tell you how much weight fraction of each compound you actually have in the production. You have date, you have other information. Another super important information is fineness that we just defined before. So you see the unit is meter squared per kilogram, surface area per unit weight, and then you have a number. Why do we care about that? Because that defines everything about the type of cement you have. And the reason is this curve, which is super, super important. So let's discuss this curve, what we see here. On the x-axis, you're looking at time. On the y-axis is compressive strength. Concrete doesn't gain a strength instantaneously. It takes a while. If you have ever worked with concrete, this is obvious to you. If you haven't, accept it. That it takes a while. If you mix it, you can step, and you can try, step over it, and there is no strength. Now, different compounds in cement, they gain strength differently. C3A, in the beginning, it has a sharp increase, but not much. But then afterwards, it doesn't contribute to a strength at all. Look at the curve as I'm explaining different components. This is C3A. Then we have C3S. This one is kind of similar a little bit. In the beginning, you have a large jump, so it helps developing early strengths. So for example, if you have a job where it is very important for you to be done quickly, it's a highway that has to be put in place, you have to open the lane very, very soon, then you want to use a cement which has this component a lot, because it gives you a lot of strength in the first few days. And afterwards, it doesn't reach a plateau as C3A. It still increases, but at a slower rate, as you can see. And then we have C2S, which is kind of, doesn't really help in the beginning, but later on, it helps a lot. So that's helpful for the long-term strength. And then finally, we have the C4AF. This one doesn't really help much to contribute much to strength. It just helps the color of cement. So, oh, sorry. Yeah, this is a, you know how steel with different carbon, I like that here. This is also one of my favorite graphs because it tells you a lot about cement. Just in one graph, you can extract a lot of information about if you see a cement, and if you look at the yield report, you immediately can make some statements about what you expect. So now we want to talk about hydration of cement, which is super important because that's behind this strength development. Cement by itself doesn't do anything. You need to mix it with water. And I have another short video to show you, which I think is much better than me explaining this. Hopefully this is. And again, these videos are a part of the lecture, so every information there is added, it's a part of the lecture.
Concrete begins its life as a fluid mixture of cement, water, sand, and ground. Concrete can be cast into molds or forms and will harden to create the necessary components of a concrete structure. The setting and hardening of concrete is caused by a chemical reaction between Portland cement and water. This can be demonstrated by adding a small amount of cement to water containing an indicator. The rapid development of blue color reflects the release of hydroxyl ions from the dissolving cement. The chemical reaction between cement and water is called hydration. The dissolving cement increases the levels of calcium and silica in the solution. When the concentrations of dissolved species reach critical levels, new solid products are formed through a precipitation reaction. This is a sketch of cement grains suspended in water. The solid hydration products form coatings around The amount of strength attained by the mixture of cement and water depends on how effectively the space between the grains is filled up. Concrete will harden within a few hours, but hydration continues for weeks, even years after placement. Here is a picture of cement particles before exposure to water. Dry cement is a fine color, and the particles are not attached to each other. After the cement is mixed with water and allowed to stand, the picture is quite different. Now the particles are grouped together and attached by solid material that provides structural integrity. Scientists at the National Institute of Standards and Technology have learned how to simulate cement hydration on a computer. Using computer simulation, hydration is speeded up to occur in minutes rather than days. Before the hydration simulation, particles of cement are arranged on a computer display. The computer determines regions of the particles that can dissolve into water. The bits of dissolved cement diffuse through the water in a random manner and react to form solid phases according to certain rules. After a cycle of dissolution, diffusion, and precipitation is complete, the computer proceeds with another cycle. As this process repeats again and again, the microstructure develops, building bridges between particles that provide strength to the material. Computer simulation has proved valuable because it allows researchers to test conditions and make measurements that are difficult to achieve in real life. At the end of the hydration simulation, the structure of the hardened cement paste is very similar to that observed under the microscope. Hydration is an exothermic process which generates heat through chemical reactions. The process of hydration can be easily followed by monitoring the production of heat that accompanies the reactions. This is done by sieving mortar from a batch of concrete and weighing it into a bottle which is placed into an insulated container. A thermistor is then embedded into the fresh mortar. The output of the thermistor can be recorded by a computer. The results of this experiment can be plotted as a curve of temperature versus time. The area under the major peak can be related to early strength development. The initial dissolution of cement produces a short release of heat.
So the way the heat is releasing during cement hydration is super important because it kind of guides us through the construction. So in the beginning, yes.
First heat in the calorimetry curve. After the initial dissolution, hydration products are quickly precipitated on the surface of each cement particle. The layer acts as a protective barrier and temporarily delays the further dissolution of the particle. This slows down the reaction for a period of several hours and is called the dormant period.
So in the beginning, when you have this hydrated layer, after a while, since you have a protection around the cement particles, the reaction slows down. And this time is the time when you would transport the material from the plant to the job site without the material sitting in your truck. So if you didn't have that, then you would get to the job site and you couldn't empty the truck because it was already hardened. So it's super important to know this shape and these characteristics of how each cement hydrates, and we know that from the rate of heat release.
The existence of the dormant period allows concrete to be transported through the construction site and placed and finished in the molds. The end of the dormant period represents the beginning of setting, at which time the cement again starts to react more rapidly with water as new hydration products are formed.
So there are two other, first of all, this has more details afterwards, and there are two other videos. They're all short. on hydration that you need to look at home. You won't be able to look at it here. So you see here, the one I showed you is the last one, and the other one altogether is just 15 minutes. So okay. This is close, not close.